Hi and hello to all of you again. So we will tackle today or discuss today medium line approximate. So from the last module or on the last lecture we discussed short line approximate. Now when we go to medium lines up to long lines, we will not discuss anymore comprehensively the vector diagram. So instead we will have another lecture there for the development of the phasor diagrams. So please stay tuned for that, and we will only tackle the important formulas and the per phase analysis circuits of every type of medium line. So before we do that, what is a medium line is all about? So the length of the line definitely will increase here from 81 to 240 kilometers or 150 miles. If you can still recall, short lines we have only 80 kilometers or less, and then from there, if your length is increased, definitely your capacitance will gradually increase as well as the voltage. So for a voltage that is above 20 kilovolt, you cannot now neglect the effect of the capacitance. So the capacitance here that is we're talking about is the shunt capacitance. So from the short line, we already have the series impedance rather of your R plus JXL or your R and L definitely, and you already have the application of your shunt capacitance. However, the shunt capacitance here must be distributed equally from the sending end and receiving end. But we have a type of a medium line which is not like that. So we will discuss that on the end condenser method. So for this, the capacitance must be distributed along the entire length of the line and distributed equally so that it can be balanced, so that you can you cannot have any significant errors on the calculations. So let us have the first type. The first type is an end condenser type. From the word itself, condenser, it means a capacitor. So for this type, it's like from the power factor correction. Okay, so you do you install a capacitor at the sending end so that you can correct the power factor at your supply or from your sending end. The capacitor always connected across your receiving voltage or your at your load. Okay, so for this, the C is connected in parallel with the load here. So it's like a short line, but here you connect a shunt capacitance. But this type of line can be a short line that is in between a short line and a medium line. Okay, so since the capacitance is not distributed equally both on the sending and receiving end, we can say that this type has a 5% error on the calculations. You can see this when you compare solutions on medium lines and long lines. Okay, this is the per phase analysis of that circuit. You have your VSN, you have your ZL, this is your ZL, you have your shunt capacitance and your load. Okay, so the relevant equations here is like you're doing a little bit of circuit analysis. So your VSN here is simply equal to your VRN simply because they are connected in parallel vectorially, by the way. Okay, so in this case, you can now get your VSN bar alpha by having your VRN again bar 0, which is your reference, plus now your IS will be different. It does not equal to I simply because your IS is IC plus IR vectorially. So in this case, you need to have your IS now vector, multiply it by ZL vector. So I did not memorize anything here. I just use circuit analysis. And then your IS can be computed. Okay, IS can be computed with an arrow sign by having the charging current plus your receiving end current. And you can still recall, your charging current can be computed by having your VRN, which is equal to your VCN, multiplied by your admittance. So in this case, we can have this, capacitance C, and then you multiply it by VRN. Okay. So if you already know your Vs and your Is definitely from the circuit here, you can now get the power factor at the sending end by having the cosine of the angle at the sending end, which is dependent on the angle of your VSN and the angle of your Is, which is whatever the bar angle that you can solve here. So, for example, you have your Is magnitude bar, I could say theta S. So here, theta Is, sorry, theta Is. So whatever your theta is here and whatever your alpha here, okay, will be definitely your angle theta S, wherein your theta S is simply theta VSN minus theta Is. Okay, thus these equations is very, very important, for determining the performance of this type of your for this type of your transmission line, which is your end condenser type. Okay, I think we can go to the next slide for your pi circuit and for your T circuit or nominal T. Please stay tuned. So hi and hello once again. So we will discuss, the second type of line, which is a nominal T approximate. So we are on medium line approximation under lesson 6, transmission and distribution. Okay, let us discuss what is a nominal T all about. So nominal T method is a method wherein the whole line capacitance is lumped at the center or at the midpoint, and the half of the admittance, half of the impedance rather, is lumped at the sending and the receiving end respectively, or concentrated on both sides. So the advantage of this is you can calculate Vs and Is using circuitry by using KCL for Is, and then you can use KVL to solve for VSM. So the advantage of having this type of line in terms of per phase basis is we can use our circuitry instead of memorizing formulas. So this is the circuit, and we consider your Y here and your ZL here definitely as divided by 2, and your Y is concentrated here. I could say 2 pi FC, or the capacitance here is lumped at the sending end, or since Y and C are in proportion to each other, so it means whatever the increase of Y will also the increase of C, simply because the equation for Y is 2 pi FC. Okay, let us have the relevant equations first. Okay, we will have VRN bar 0 as our reference in this case. So if you want to get VCN here, okay, you need to have VRN bar 0, which is our reference, plus whatever the value of your IR here, and then it will dependent, on the angle, on the power factor, and multiply it by ZL over 2, which is the constant, of the transmission line. Okay, now if you already get VCN, in this case you can now get IC. So your IC here is definitely from the equation of your current, charging current. This is from power factor correction, is J times VCN multiplied by the admittance Y. Okay, wherein your Y is definitely 2 pi FC. Okay, now if you already get IC and IR is already defined from the given, you can now get your IS. So IS by KCL, at this topmost point here, or node, I could say node X. Okay, your IS simply equal to IC plus whatever your IR here. Now you can now get your VSN with the transmission angle alpha, which is simply equal to whatever your VCN here. I could say you have an angle theta C. Okay, so we can have this one as VCN bar theta C. Okay, plus whatever your IS here, and then ZL all over 2. So the answer here, for example, is IS with an angle of theta IS, whatever the angle that it will yield. So your VS here, bar alpha, is this result of the this equation. Now you can now get the power factor descending in by having the cosine of theta S, which is dependent on alpha, and theta IS. So definitely cosine theta S is theta V, or your alpha, minus whatever your theta is here. And if you want to consider, it can be a lagging or a leading power factor. So it will depend on the phasor diagram. On the phasor diagram, a lagging condition means IS lags PS by a certain angle theta S, or in a leading condition, IS will leads PS by theta S. So what I have already given to you this in terms of relevant equations is from the circuit, and then from our analysis from our former modules or videos that we have discussed so far. Okay, we will now discuss nominal pi in our next video. Stay tuned. Hi, and hello once again. So we are in our third type of medium line. So we have the nominal pi method. So from our previous discussion, we discussed an end condenser, we discussed a nominal T approximation. So today we will discuss a nominal pi method. So in this method, the difference is the capacitance of the conductor is divided into halves. So the half will be allotted to the sending end, and the half will be allotted to the receiving end. And the ZL is lumped on the middle. Your ZL here again is your resistance plus your JXL, and your capacitance here, which is designated by your admittance. Okay, which is you need to divide it by 2. Okay, now this type is the most common type and a typical type of a medium line, and it is used on power system simply because a nominal pi can be simplified further to a short line, which we will discuss a little bit, or we can already do this, in this case. Now, if this is your PPA, or per phase basis, okay, it's pretty clear that the voltage at the sending end is also the voltage at your capacitor at your first capacitor. The voltage at the receiving end is also equal to the VCN2 at the second capacitor, or voltage at the capacitor here. So in this case, you can have a more simplified. So this is the simplified SLD, that you can have a short line approximate for this case, wherein this is your VRN is equal to VCN2, your VSN is equal to VCN1, right? And you have your IL, and you have your ZL here. It's like a short line approximate. So that's why when you have a power system analysis and you're considering load flows, the model of the line always in nominal pi. Okay, so for this we can now establish relevant equations since we already have these two. Okay, so first of which you need to have, okay, this is IC2 by the way. This must be blue, sorry. Must be IC. There's an arrow sign here. Yes. Okay. Now, you can now get first the IC2 here. No? So your IC2 can be computed by having J VCN or VRN in this case, because VRN is equal to VCN 2 multiplied by Y, wherein your Y is 2 pi FC. Okay, please take note, if you divide the Y by 2, you need to divide the capacitance by 2 as well. Okay, this is the first equation here. Okay, consider this one as 2 pi FC. So, since Y is proportional to C, if you divide the C by 2, the Y must be divided by 2, like this. Yeah. Okay? So, to avoid confusion, I erase the 2 here, they divide by 2. Now, if you already have your IC2, we can now get your IL by having IC2 plus your IR. Your IR is already a given here, considering the angle negative and positive theta r. And please take note, the negative here is a lagging condition and the positive here is a lead condition. So lag, sorry for that, LAG, lead condition. Okay, now if you already have IL, you can now get your VCN1 here by having, okay, whatever your VRN, which is your reference, plus IL, and then multiply it by ZL, which is your R plus XL. If you already get VCN1, you can now get IC1 here by having J VCN1, okay, and then you have YL over 2. Now, you already have IC1, you can now have a KCL at this point, top point here. Okay, this is KCL, for example, at X. And this is KCL at Y, for example. So, you will have your IS here as IC1 plus IL. Now, you can now get the, definitely here by using this relationship that you have your VRN, since this is reference, plus IL ZL. So, you can have here VSN bar alpha, your IS here, you can have IS bar theta IS. Okay, so you can now get the power factor now. So, I will use a red pen. So, the power factor descending in is definitely cosine of theta S, wherein that is alpha, theta B minus theta IS. Okay, and then, considering a lagging condition, IS must lags VS by an angle theta S. And if considering leading, IS must leads the voltage by an angle theta S. This theta S. Okay. So these equations is just based from this per phase analysis of a nominal pi. And the nominal pi is the most practical medium line approximate that is being used on a power system. Okay, so we will discuss now on our next slide or next video, long lines, an interesting problem, especially the rigorous method or the real solution. Stay tuned.